Hi, okay, so this is work solution 11, and it's kind of imagining that we've already found the neutral axis and the second moment of area for this sort of thing that looks a bit like a T-beam. So let's see what that data is. So we got a neutral axis from there, the centroid, to the base. So we've got a certain distance there. We can add up these heights, these depths I should say, and then work out, take the depth away from that neutral axis position and then work out what that distance is. The significance is that y is going to be the vector difference away from whichever direction you applying the load. So if we was applying the load from above, y should be pointing away from that neutral axis. What we're doing here for this problem is we're using the engineer's bending equations. So m over I, stress over y, and E over R. On the whole, we're not interested in the last column of that data. That we could use that to make rough calculations for deflection, but we're interested in the stress caused by bending from the load. The y, in this case, where we got the load from above, so that's the y that's going into that formula. So that y could be pointing to the bottom, imagining that we've got a load from the above, so we're going to have a stress that's in tension. Or the y could be going in the opposite sense, so we get a negative value, and then it'd be in compression. So the engineer's bending equations we rewrite, usually because it's the term that we're usually interested in, to something called the flexorial equation. And this is the way that we normally would be applying this equation to work out what the stress is. So the m I get from my bending moment diagram. The I I've calculated by using a tax form and trying to work out the second moment of area, and the y I come back to my geometry and decide what y I'm looking at. And as I said, I'd probably be looking at either the y at the bottom or the y at the top. Normally we're interested in the maximum stress, so we're normally interested in the biggest y. So that's going to be the y from the neutral axis to the bottom. Let's go over this problem. So this problem, after finding well, we've already found the neutral axis, we're now going to find the distance to the top. So we can compare these two numbers now. It's fairly obvious which one was going to be the larger. But we can see that this is going to be our larger number. So if I was simply just interested in terms of stress and the structure of this problem, I'd be looking just at this using this y in the engineer's bending equation or flexorial equation. So a positive bending moment causes tension on the bottom and compression on the top. You're going to have to go back and think about what we mean by that in terms of the UE convention that we're using. So we're going to put a load on top, and we could then sketch what a shear force diagram would look like. So that would create a positive reaction there, positive reaction there. So the shear force diagram looks like that. Okay, so that's my V against X. And then the bending moment diagram, well, the quick way to do it is to say, what's the area? It's a positive area, so we're going to integrate that. This is negative, so we come back down. So we get maximum M bang in the middle, as we would expect. So we're going to get maximum stress in the middle, and notice that this is a positive value. So this is what this statement's saying here. If you have a positive bending moment, you're going to have a load from above. That load from above is going to cause this thing to be pulled out from a bottom and come in from above. So we're going to get tension at the bottom. A negative bending moment causes compression on the bottom and tension on the top edge. So if we had the reverse going on, if we had the load coming from above, or some kind of force coming from above, what would be an example of this? We would probably have maybe a force. We could then have loads maybe doing something like this. So the loads would then cause this beam to hog in that sense, and then we'd get compression on the bottom and we would get tension on the top. Okay, so that's going to be the less likely case, I suppose, for a simply loaded beam. Calculate the maximum stress at the section for the edges. So calculate what the stress is going to be there and there using the flexorial formula. So let's recall what that is again. So that's stress equals m over I times by y, and y is the distance away from the neutral axis where we've got sagging for this case. Let's go for a nice green. And y will be pointing off in this direction if we had hogging. So if the load's coming from above and the beam is going to be doing something like that, then it's hogging. Sorry, I said the wrong thing there. If we've got forces coming from below, which might cause this to hog in that sense, whereas the sag, we're imagining we've got a force from above and maybe between two pivots like that. So that's going to cause us a sag effect. So with the red, the y will be pointing downwards, and we've got a hogging situation, and the green is going to be pointing upwards. So we do it opposite, whichever way the bend we can imagine. So we're going to bend it like that, then it's going to go up, bend it like that, then it's going to go down. The reason for that then is that we can use y here. If we've got a y value, we're going to have a positive value, whereas if we go back a bit, we'll have a negative value. So that tells me that that is in compression and that's in tension. However, for a hogging setup, we've got this in compression and we've got this in tension. Okay, so whichever way we're going, we'll be using this formula here. Stress equals m divided by I times y. So m is the magnitude that you're going to be reading off from your bending moment diagram. Y is the distance from the neutral axis, and it'll go to the top or the bottom edges, and I is your second moment of area. So let's imagine the case we've read off from our bending moment diagram that we've got a 200 kilonewton meter positive bending moment value. So on my bending moment diagram, I've read off this 200 value. So that's then going to give me my m. value. The I value is what I've found before. Okay, there's a typo there. We're working, I can see, we're working here in meters, because we've got 10 to the minus 12 there. And we've converted the millimeters into meters. So make sure that if you've got a result in terms of meters to the power 4, you're going to be using your Y values in meters as well. So this tells me we've got a positive load, sorry, you've got load from above, positive, which causes a positive moment, which will cause me compression at the top. Okay. And now I can look for the tension on the bottom. Now if we had the opposite case, we've got this hockey diagram here. We're going to have 100 kilonewton meters. In this case we're going to cause a negative bending moment. Okay, so we've got so this is read off the diagram and we're reading a negative bending moment value. So that's the value going into the M. Right, so this time we should be saying that Y is going to be going away from us in that sense. Now I'm looking for the value on the bottom here. Now I could, because Y is going up here, I could put a minus here, or I could just emphasize its compression, and this particular solution is just emphasizing its compression. So wherever you have the minus there is neither right nor wrong. Okay. And put those numbers in your calculator and we end up with that result. And for the top, that's been pulled apart more, so we should definitely have a positive result there. And we've got a so that's my bending moment value, and these would be found independently before we attempt these kind of questions. There we can work out how much stress there is, and that's it. Okay.